Today we are going to learn soil compressibility, which is chapter 11 in your book. So I already posted the review worksheet as well as the solution in your blackboard, but now I'm going to do all those problems here and try to explain a little bit better. But still, if you don't understand, you can definitely Skype me or also FaceTime me so that I can explain that one better to you. But I'll try to do and try to explain everything very elaborately so that you can understand everything. Now, before I start this worksheet, I'll talk like two issues which is very, very important to understand the compressibility of soil. First of all, you can see here, I wrote already down here, that normally consolidated soil and over-consolidated soil. So what is normally consolidated soil? Normally consolidated soil means the soil at its loosest condition. Means like the soil was never been compacted other than the self-weight of the soil. So this is the loosest condition. In practical case, it's very difficult to get normally consolidated soil because somehow it has to be compacted a little bit. Maybe a little bit, but most of the time it's very difficult to get soil which didn't compact other than its own weight. On the other hand, the over-consolidated soil means the soil which has already been consolidated or compacted in the past, and now the force is not there, you don't see that one, but you can see the soil is a little bit more compacted than the normally consolidated soil, and that doesn't undergo that much settlement. Let's say, for example, so let's say there is a hill here, and one of the contractor thought that that might be a good subdivision, and what he did, he just cut some portion of that hill here and started making houses here. Now, at a time you just went there, which is, let's say, 3 feet below that soil surface now. So we can say this is your actual grading. Or natural grading. I should rather say natural grading. And this one is your finished grading. Now let's say if you think about the distance from here to here that has been cut maybe like 20 years back, that let's say this distance is 7 feet here. Now, if the soil unit weight is, let's say, 100 pound per cubic feet, then the current overburden stress here, because it's not there anymore, so current overburden pressure is actually gamma H. So 100 into 300 psf. But if you think about the past, many years back, maybe 20 years, 30 years back, when the contractor did that one, maybe you don't know like that there was soil down there. But you can see, if you get the papers out there, other land records and everything, and you realize that actually there was another top 7 feet above that finished surface. So your pre-consolidation pressure or pressure in the past was actually gamma H1, let's say this is 100 into 10. So this soil in the past has been compacted with 1000 psf pressure. And now you took that load off, so what will happen, because the soil is elastic plastic, so it's not gonna go back to its original location. It's just gonna swell a little bit more when you take that load off, and then when you put like 1000 psf load again, then basically this one will compact very little, like compared to normally consolidated soil. Now let's talk about what does it mean in terms of compressibility. Let me show you an example here. Let's say I took two soil columns. At the beginning, let's say both of them are normally consolidated. Okay, so at any point this is normally consolidated, means the loosest condition. And I made that one just, like the put soil particles very slowly so that only they can take their own weight. So they are very actually loose soil here. So both at the beginning, both of them are normally consolidated. Then I pressure that soil, maybe let's say 100 kPa pressure. So what will happen when I apply that pressure? This one will come here. Now if I take the soil, take the pressure off, this soil is not gonna go back here because soil is not completely elastic. So the soil will just go a little bit up here because soil is elastic plastic. So after taking that pressure off, then basically you will see that the soil has rebound from here to here. Okay, so now this is a normally consolidated soil and this is a over consolidated soil, and the pre-consolidation pressure is 100 kPa. Now if you think, like if I apply load here and here, that which soil will compress higher? Basically this soil is the loosest condition. This soil has compacted a little bit with the pre-consolidation pressure, so the compressibility here is much higher than the compressibility here. So that's basically the implication of normally consolidated and over consolidated soil on settlement. Now I'll talk another topic which is very also important, which is called the effective stress and total stress. Okay, so effective stress means like how much stress is taken by the soil. When you apply total stress in a soil mass which is saturated, in that case you will see that the total stress will be divided into the soil as well as in the pore water. Okay, so let's say, and the relationship between these two is your total stress sigma is equal to your effective stress. So we have been talking about the effective stress, right? So if you see the relationship between total stress and effective stress, then total stress is equal to effective stress plus pore water pressure. So the total stress will be distributed in water as well as in soil. Now it depends on how much stress is going to water and how much pressure is going to the soil depends on the drainage situation. First of all, the soil is very compressible. On the other hand, the water is mostly incompressible. So basically the stiffness of the water is much higher than soil, so you will see that water will try to take most of the weight at the beginning before it drains. Now you can see here, let's example, like this is a column, reinforced concrete column, and there is reinforcement here, and this is concrete. Now if you apply any load here, so you will see that total load will be distributed in the concrete as well as in the reinforcement. And you will see the pressure in the reinforcement or stress in the reinforcement would be much higher than the stress in the concrete, because the stiffness of the reinforcement is almost 9-10 times higher than the stiffness of the concrete. So same thing happens here. When you apply load to any soil mass, soil, and if it is like completely saturated, then there is basically water which is kind of continuous through the pores of the soil. And if you try to compress them, then basically initially all the load will be taken by water, because the water is kind of almost incompressible. So when the water is stressed, they will try to get out from that domain. So that's called the drainage, that how fast they can get out from there. We know that for sand, the hydraulic conductivity is very high, so they can get out from there easily. On the other hand, for clay, the permeability of the soil is very low, and that's why you will see that the water is draining very, very slowly. So basically that would take longer period to escape all the water. Not all the water, some of the water, because of that consolidation. That's actually called the consolidation settlement. Any settlement of a saturated clay layer due to expulsion of water from there. Excess pore water pressure has to be 0 before final, settlement. So basically you will see that the beginning, when you apply any load to a soil mass, this one will take all the load first, and then this one will try to escape from there. So you will see this one is becoming close to 0. On the other hand, at the beginning this one has to be 0, and this one is, with the time when the final consolidation settlement will occur, then this one will take all the load. So that's basically the understanding of effective stress. Now I'll show some of the problem here which I included in your worksheet, and as you do this problems, then basically you will be more clear on these issues. So let's start our worksheet. Number 1. This one is showing let's say that's the finished or existing grade. and this one is your original grade. Now you collected some soil sample. This is actually, like you cut that hill and make a subdivision here, and you constructed buildings here. And let's say this is your finished grade and you were trying to get some soil from here, which is 8 feet below, and you realize from the past records that actually the original grade was much higher, and that was actually here, which is 30 feet from there. Now the question is asking that the over consolidation ratio, OCR. So we know OCR means over consolidated ratio is equal to pre-consolidation pressure divided by current overburden pressure. Okay, so what would be the current overburden pressure here? There is no water table, so we don't have to think about that. Basically, the total stress would be equal to the effective stress because the soil is not saturated there. Okay, so the overburden pressure here, current overburden pressure would be, let's say they gave you the gamma of that soil, which is 110 PCF. So current overburden pressure would be gamma H, which is 8 here, that's the current overburden pressure. Okay, so in the past, what was the maximum pressure this soil has experienced? If we assume that there is no other force, like try to compact that one other than the weight of the soil, then basically we can find out our pre-consolidation pressure, which is again gamma, let's say H1, so that would be 110 multiplied by the total height here, which is 38. So that's actually 4,180 PSF. So my over consolidation ratio would be 4180 divided by 880 is equal to 4.75. So the answer is E. Your over consolidation ratio is 4.75. Okay, let's move forward. Problem number 2. So problem number 2 is saying the state of stress of a soil element is shown below. So you are trying to you have soil here, and with the piston you are trying to apply a pressure here, which is, let's say, sigma equal to 10 psi. And then you have a pore water pressure measurement transducer at where you can find out the excess pore water pressure. And let's say you got that one at a particular time when you allowed them to go some water out from there. Then you will see what will happen like when you actually there is no drainage here. When there is no drainage here, then basically at the beginning all the pressure, total pressure you were applying into that soil mass would be taken by the water itself. So you will see that pore water pressure would be here 10 psi. So in that situation, your effective stress would be 0. Means like actually soil is not taking any stress at all. Now what will happen, since the water is stressed, they will try to escape from that domain. So if I open that one here, basically in nature, it's not a closed system. It's always an open system. Water can, seep through the other layers and try to escape that one, escape from there very easily. But sometimes it depends on how fast they can go. For sandy soil, it will go very fast, and the primary consolidation settlement will occur instantly. On the other hand, you will see the Hadley conductivity of clay soil is very, very low, and that's why this one will take more time, for consolidation. Okay, that's the basically difference between these two types of soils. Now, if you allow then the water here, then some of the water will try to escape from here. And in this particular problem, number 2, it's saying that at a certain time, the pore water pressure is 4 psi. So what would be the effective stress? Very easy. You can see your effective stress at that time would be total stress minus pore water pressure, which is 10 minus 4, which is 6 psi. So it means like the soil will take 6 psi load, the water will take 4 psi load, so the total is 10 psi. So when the consolidation will completely occur for this particular load, then basically you will see the soil is moving from here to here, and this one will become 0 after completely, the normal consolidation will be completed, and this is basically your settlement at that time. Settlement at that time. Now what happens like if you want this one comes here and then you will again apply another 20 psi load. So as soon as you apply the new load, 20 psi load, basically at the beginning this one will be 20 psi and some water will try to go from there, and over the time the water will escape from there, and that 20 psi load will be taken by soil. And you will see that this one has moved actually here during that time. So that's the way soil try to consolidate, especially like the clay soil when this one is saturated. So anyway, so this is your answer, which is actually, that should be G, actually it should be B. Anyway, 6 kPa load. Now the number 3 is saying that if the excess pore water pressure is measured 0 after a certain time, then it can be assumed the clay system is not completely saturated, primary consolidation has finished, effective stress is equal to your total stress, and B and C and A and B. Now you can just read the answer here and you will get the explanation for that. Okay? And the first one is saying that the clay system is not completely saturated. If the clay is not completely saturated, then the settlement, we don't call that one uh, primary consolidation settlement. We don't call that one, okay? Non-saturated, for non-saturated soil, this term doesn't apply. Anyway, let's move forward. Number 4. A soil profile is shown here. So this is basically your clay, and you just put a piezometer here. So this one is saying that the new foundation will be constructed on top of the soil here, top of the soil here. The pressure from the new consolidation, del sigma prime, is 500 ksf. Now it's asking, so you can see before applying that load, this is your water table, so water will be here. As soon as we apply the load from the foundation, actually you will see that pressure will go up, high. Now, if you apply, let's say from a foundation here, if you apply new load here, which is 500 PSF, then at the beginning, just after applying that load, who is going to take all this load? Definitely we know from the theory that actually all the load would be taken by pore water pressure. So you will see that piezometer here which measures the pore water pressure. So all of a sudden this whole thing will be taken by your pore water pressure. We call that one excess pore water pressure. So this is the initial pore water pressure, then now you see the excess pore water pressure because of this pressure here. So this height here, that would be equal to, you know, that at the initially at time t equal to 0, you will see that del sigma prime is actually should be equal to your pore water pressure. Okay, so this one has to be 500. So if you change that one, your gamma H, pore water pressure, is equal to 500. Then your H would be 500 divided by gamma water. Which is kind of 8 feet here. So what will happen, the water, as soon as you apply the load here, this you will see that level of water has moved from here to here. Okay, and then what will happen? Then basically the soil will try to drain this way because it cannot go here because this is impervious soil. So all the water will try to go this way here, and As soon as the water starts moving, the soil will try to consolidate it, means like this excess water pressure will move slowly from here, and all the way here when your excess pore water pressure is 0. This means like your consolidation settlement has completed, uh, and for this particular load though, the consolidation settlement occurred for this particular load. Now if we add more load, then basically this one will start again consolidating the soil. Anyway, so basically this is your answer.